So hello everyone, and thanks for joining this tutorial. I'm Yiran Luo, and I'm currently a postdoctoral associate at the Department Geomatics Engineering, University of Calgary, where I obtained my PhD degree. And I also had a joint PhD in information and communication engineering from the Beijing Institute of Technology. I was a postdoctoral fellow at the Department of Aeronautical and Aviation Engineering, the Hong Kong Polytechnic University. I have had many years' experience in advanced GNSS receiver design, super resolution GNSS signal processing, and remote sensing, as well as the navigation and positioning in harsh environments, such as indoor and urban positioning. Today, I'm going to do a tutorial with the topic towards accurate absolute indoor positioning, super resolution, global navigation satellite system receiver technology. So this tutorial will not focus on the basic knowledge about GNSS receiver design. Instead, the techniques related to a new receiver design for the indoor GNSS will be the primary contents, so which is very highly to our latest research work. Now I will start with the first part of this tutorial. I will give a brief background of the indoor GNSS. So as we know, the global navigation satellite system mainly consists of the GPS of USA, Beidou navigation satellite system of China, Galileo of the European Union, and also GLONASS of Russia. So the GNSS satellite number is larger than 100, which means it is more than enough to provide global positioning service. So the GNSS receiver receives radio signals and estimates its time of arrival. Then it produces GNSS measurements like accelerant carrier phases to provide high accuracy all time or weather absolute positioning in the Earth's coordinate frame. So today, the GNSS is ubiquitous in several fields and industrial fields, such as personal navigation, the Internet of Things, also precise agriculture, geomatics engineering, environmental sensing, etc. But however, for the indoor cases, the indoor GNSS applications are still very limited. So one must be very interested about these questions. So what's the challenges of the indoor GNSS? Are there opportunities for it? Or what's the core techniques to achieve an indoor GNSS receiver? The latest GNSS market report from the European Space Agency forecasted that in the next 10 years, the annual shipments of the GNSS receivers will constantly grow. So these shipments will be heavily dominated by the consumer solutions, tourism, and health segments following the wave of global smartphone or wearable sales. So although it means that even more the installed base of the GNSS device will be dominated by the smartphone or wearable sensors. So this fact brings increasing GNSS indoor cases. However, we know that there are some other sensors can also help the indoor navigation, but only for the GNSS devices, because every single smartphone today has a GPS or GNSS chipset. So developing indoor GNSS receivers will demand few external instruments, labor costs, serving costs, or patent fees, etc. So we can see that it is very urgent to develop indoor GNSS. So for the next part of this tutorial, I will explore the fundamentals, challenges, and opportunities of indoor GNSS. So one must be very interesting to know why is it hard for the indoor GNSS commercialization. So for the technical issue, it is very extremely different from the traditional GNSS baseband if we would like to achieve an indoor solution. For example, because we have to deal with weak signal reception and very severe multipath interference, and also the near-far effect. So but for this tutorial, we will mainly discuss about weak signal reception and multipath. For the next issue is about a practical realization, because we may need some external adding, such as aided GNSS to provide bit size streams, also the high accuracy time synchronization. In this tutorial, we may discuss that the pioneer channel of modernized GNSS signals can remove the bit size, and also we will mainly focus on the light indoor results in this tutorial. So the high accuracy time synchronization may not be our main issues here. Another problem is that customer issues. We know that it used to have a few demands for the indoor GNSS, but it is currently very high and will constantly gain, as we discussed in the earlier slide. So due to the signal blockages, refractions, diffractions is central, and the indoor GNSS is very weak to be received, and also due to the very super long transmitting distance between the satellite and our ground GNSS receiver antennas. The right figure shows that the baseband correlation power distribution of indoor GNSS. So compared to the designed power peak, it is much tricky to detect the power peak and estimate the unknown signal parameters in this case, indoor cases. So the signal strength is sharply attenuated, and the useful signal is varied by the noise power. But can these problems be solved? This tutorial answers yes. That is, we can use longer received signal sequences to accumulate signal power and elevate noise power simultaneously. What does a longer sequence mean here? I will firstly introduce a general GNSS signal model. The GPSL1C signals will be taken to be an example here. At the right side of the slide, here's we give a received radio frequency GPSL1C signal model here, at the left side, and at the right side, here's the general structure of this signal, and it is a carrier signal which is responsible for the transmission of the signals in the space. And here's also the data streams, and it carries the ephemeris of the signal sending time, as well as some no-error models to achieve the positioning purpose. And the third layer of the signals is the spreading code. It is responsible for the time of arrival estimation. All of these three components forms the final GNSS signals here. And so what is a long signal sequence? How it can be used to achieve a long integration? For example, for a traditional integration method, that the usually sequence within 1 to 20 milliseconds were used to estimate the unknown signal parameters. But for a long integration strategy, you can see here a very long signal sequence will replace the shorter ones, and then to achieve a very long integration performance. But however, once we would like to use these techniques, there are some extra problems that we will meet. So a pretty much tricky practical issue will arise once this is used. More specifically, when the received signal is correlated with a local replica, the transition of the data bits that is modulated in the GNSS signal will cause terrible attenuation in the signal correlation gain. Here, and we see that this gain is terribly attenuated here. But fortunately, such an issue can be solved by some means. For example, once we can know the bit time in advance, it can be directly added to the local replica and get the bit transition removed. After that, the normalized gain will not be attenuated anymore. Here, and we can see that the gain turns back to be 1. So regarding the bit transition problem, the pioneer channel of the modernized GNSS signals is natural to remove the bit time in the baseband processing. So at first, different from the known database, a known secondary code sequence is modulated in the signal of pioneer channel. In this case, the bit transition can be removed. So accordingly, a long coherent integration can be realized without borrowing with the bit transition problem now. Besides, the GNSS modernization brings plenty of signal sources with pioneer channels today. Here we list current open service modernized GNSS signals with the pioneer channel. So we can see that for the 3 main constellations, they both have their own modernized signals and with pioneer channels. So it can be said that the modernized GNSS signals are born to implement non-coherent integration. This tutorial mainly focuses on the GPSL1 signal and will give some preliminary experimental results based on this type of signals. Now, so we are supposed to know the wake signal reception for indoor GNSS can be processed with LCI, that is long coherent integration, and the bit transition over the LCI can be coupled with the bi-pioneer channel signal. Then it is time to show how the results of the indoor signal power improved by this method. For example, at the right side of this slide, this is the traditional a correlation power that based on a short integration time, that is 2 milliseconds. After we use a long coherent integration for the L5 pioneer channel signal, we can see that the power peak has been enhanced, and this time is 20 milliseconds. How about we continue to enhance this integration time? Yeah, we can see once we increase the time to be 100 milliseconds, not only the signal power is further increased, but also the side lobes and also the noise powers has been elevated. So the multipath interference is the other tricky issue following the wake reception for indoor GNSS. Here the code autocorrelation function curve is given in this slide. So where the line of sight and the long line of sight signals are in, this is the line of sight loss signal, and this is the long line of sight signals. The combined signals, namely the multiple signals, is also shown here in the blue lines. Commonly, the early and the late channels correlation gains will be used to form an estimator of the TOA or the code phase error. So the red curve corresponds to the code error model for the no signals estimation here. And in indoor cases, the unknown signals will be overlapped with the lost signal, so which will cause the error estimator to be distorted. It is shown in blue lines here. This case will lead to a biased estimation of the code phase. More specifically, see the 0 point of this x-axis, it points out that 0 when the input error is 0. However, when the distorted estimator outputs a value that is not equal to 0, like this. Summarily, multipass effect causes biased TOA estimation here. So this slide compares the code correlation curves regarding different Doppler frequency offset between the open sky and the indoor cases. A standard curve can be formed in the open sky case through baseband processing corresponding to the nominal cloud phase and the Doppler frequency. Undoubtedly, the indoor case becomes much worse. For instance, the loss and unloss envelopes are overlapped, which makes the signal estimation difficult. It is shown like this. So, is it able to be solved? So the next slide will answer it. A previously published work will be taken as an example to show how the non-coherent integration works for the multipass mitigation. Before extending the coherent integration time, the loss and unloss signals are overlapped. After a non-coherent integration is used, the loss and unloss signals are separated. It can be simply explained that the frequency difference between the two signals are very close to each other. Then a higher frequency resolution is required to identify both of the two, which is realized with the super non-coherent integration. So super non-coherent integration can mitigate a multipass. But extra problems rise due to the use of the super non-coherent integration. That is SLCI. So next few slides, I will discuss them. Here we take the code signals and example just for simple analysis and easy understanding. It should be noted that these examples are also applicable to the GNSS carrier signal. A desired normalized correlating gain based on a perfect match between the received and the replicable signals. The gain value is supposed to be 1. Nevertheless, there are several factors in the SLCI that will reduce the gain. So next slide will discuss the absolute code phase error. The absolute code phase error means that there is a misalignment between the received and replicable code phase. It will result in a correlation attenuation. So another aspect is the frequency shift error. Once the frequency shift is not well estimated in the SLCI, it will also cause a correlation attenuation, like this. The frequency rates, that is the change of the frequency shift, will be more tricky. So the Doppler rate always occurs to the received GNSS signals due to the user's motion and the clock oscillator jitter. It can be processed in the traditional, it cannot be processed in the traditional GNSS baseband processing methods. Right now, can you imagine what will happen to the real received signals? Yes, the mentioned 3 issues occurs to the real received signals at the same time. In other words, severe attenuation will happen to the SLCI correlation if these issues cannot be well processed. Here are the summary for this section. We have discussed the indoor GNSS receiver challenges, and the 2 main challenges are multipass interference and weak signal reception. Then we mentioned that the non-coherent integration can deal with these issues simultaneously. Another issue will occur when the non-coherent integration is implemented. That is the bit transition problem. The aided GNSS technique, non-coherent integration, and also parallel channel of the modernized GNSS signals can solve this problem. Another issue is that the loop filter limitation. For example, usually a loop filter is designed in the traditional GNSS receiver just to remove the red noise and provide higher quality GNSS measurements and then output a higher accuracy positioning. But for a loop filter, it is designed in the analog domain, and it is also digitalized by means of mapping function. So the loop filter will only stay stable when the product of the bandwidth of the loop filter and the coherent time is much less than 1. So the loop filter used for the traditional receiver will not be available to the SLCI baseband processing. So to the answer to this limitation is we can use an open loop or bench processing to solve it. Here, based on the open loop and non-coherent integration, and we also meet the frequency shift error problem, and it can be reduced by a faster Fourier transform implementation in the baseband as well. And also we know that the signal dynamics, that is Doppler rate, will happen to this architecture. So to the best of my knowledge, there's very few research works related to the answer how to deal with the signal dynamics in the baseband processing. Another problem is the absolute code phase error problem. Current researchers have proposed that the phasor and also the absolute position aided algorithms can deal with this issue. For this tutorial, it aims to achieve indoor GNSS receiver that can provide accurate absolute positioning. So we use a very super long coherent integration to mitigate the multipath effect and to help the weak signal reception. Then we use the parallel channel of the modernized GNSS signals to overcome the bit transition. And we adopt a snapshot baseband to deal with the band limitation problem. And we adopt the digital fractional Fourier transform to compensate for the signal dynamics in the non-coherent integration. And finally, we propose a maximal likelihood estimator to estimate the frequency shift error, Doppler rate, absolute frequency error simultaneously. And also it aims to reduce the computational load of the digital fractional Fourier transform. Here's the reference for the previous slide. Here we list the representatives of startups focusing on the new GNSS receiver design. They are focusing on the new techniques discussed earlier for indoor GNSS signals. For example, a focal point positioning use super correlation that is very similar to the SLCI mentioned before to achieve high accuracy positioning based on the wearable smartphone devices. And this company has designed a deal with the U-Blocks company that is the world leading GNSS chip manufacturer. So another company is OneNav that it aims to use pure L5 or hybrid L1 L5 to achieve high accuracy urban navigation. It has landed around $21 million in Series B funding and bringing total funding to $33 million. All these startups can be the proof that it is time to step into indoor GNSS. So based on the previous introduction, one may be very curious to know how a new GNSS receiver architecture will be like by leveraging the SLCI, FRT, and MLE for indoor positioning. For the remaining parts of this tutorial, I will focus on this point, namely the super resolution GNSS receiver techniques and some preliminary results based on the prototype. Before the introduction of the new receiver architecture, I hope to define the super resolution. In this tutorial, the super resolution refers to the inverse problem of recovering fine-scale information from low-resolution measurements. Regarding GNSS signal processing, we would like to use the super long coherent integration to improve the standard coherent integration or the traditional long coherent integration to improve the baseband measurements such as correlator. Then we aim to achieve very high accuracy positioning results for extremely challenging cases such as indoor situations. This slide shows the general architecture of the traditional GNSS baseband tracking. Again, this tutorial will discuss a new receiver use SLCI. The loop filter algorithm cannot be available anymore due to bandwidth limitation, as I mentioned before. So commonly, an open loop tracking architecture is the candidate to deal with this issue. So this slide shows the typical open loop tracking architecture here. Simply speaking, this architecture is more likely to be an acquisition process. The difference is that the finer search grids regarding the code phase and the Doppler frequency are adopted to improve the GNSS measurements for reliable and accurate positioning purpose. But still, the long coherent integration in this architecture is still not long enough for indoor purpose. Now this presentation will review each block of the new receiver one by one in order to achieve accurate indoor GNSS positioning results. At first, the SLCI will be used here, and the primary difference between the new architecture and the traditional open loop architecture is that the same Doppler frequency tunes the local replica of the former one through the NCO. In contrast, the open loop is adjusted by a bunch of different Doppler frequency values. If once the SLCI is assumed to be matching filter, each of the sub-correlators are the partial matching filter here. The SLCI is not adopted in the baseband now, so we need to have a recap of the issue from the SLCI. Seeing the curve here, the extent of the Doppler rate in the received signals will cause a more significant frequency error and carrier phase error, like this. So if it cannot be compensated in this LCI baseband processing, the purpose of the accurate indoor positioning will not be achieved. So this point was seldom worked in the GNSS signal processing field, to the best of my knowledge. This tutorial comes up with a way to deal with signal dynamic problem mentioned in the previous slide. At first, we improve the traditional baseband model as follows. More specific, we consider an extra Doppler rate term in the model. Then we apply the analytic estimator based on the digital fractional Fourier transform to estimate unknown Doppler rate parameters. It is estimated based on the matched rotation angle of time frequency plane. So the other parameters in this Doppler rate estimator is the number of the partial matched filters and the sampling interval. So the diagram of this slide aims to show how the digital fractional Fourier transform is implemented to match the dynamic signal and compensates for the power loss. For example, the traditional 2D correlation search plan, including code phase and frequency shift, are improved by a 3D search process where a subspace that relates the Doppler rate related to the Doppler rate search is ended. The Doppler rate matching filter relates to a rotation of time frequency plane. This is the correlation power that is detected in the traditional search plan. So after the rotation of the time frequency plane, that is the process to search the Doppler rate. It can be found that once the Doppler rate is matched, the power loss of the SLC dynamics is efficiently compensated. It means that the traditional search space will not be available for the long coherent integration. The super long coherent integration, but the improved model will be efficient when the digital FRT is adopted. Based on these discussions, the digital FRT block is ended after the SLCI block in the new receiver architecture, where code phase error, Doppler shift error, and Doppler rate are considered simultaneously. So the GPSL5 intermediate frequency data are collected in the real world to verify the SLCI and FRT-based receiver. Comparing the correlation power before and after the digital fractional Fourier transform, it proves that the FRT denoises the SLCI correlated output. Besides, it improves the upper bound of the signal estimation, or more specifically, the positioning accuracy. Before the introduction of the next baseband processing block in the new GNSS receiver, let's again have a review of the absolute code phase error issue. Here's the perspective of the baseband processing. So we directly give the definition of the markers here at the upper right corner. So we will give the definition without explanation here. The white circles correspond to the estimated code phase, while the red pentagrams is the reference computed from the true position, the known error model, and the fitted clock bias. The absolute code phase error due to the unknown causes a large difference between the estimation and the reference. Once it is removed, this difference error can be corrected. So for this part, from the positioning perspective, when the absolute code phase error is removed, biases of the absolute positioning results are radically reduced as well. For thorough consideration, a maximum likelihood is ended following the digital FIFT block. As a supplement of the previous two blocks, it helps to estimate the absolute code phase error and reduce the computational load based on the closed form SLCI correlation model in the fractional Fourier transform, fractional Fourier domain. In this slide, we can clearly note that the measurements locating at the extra subspaces related to the Doppler rate can be used to optimize the signal estimation. So based on the analytic expressions in these subspaces, as well as Bohr correlations in these various subspaces, the SLCI baseband MLE can be built. Then Doppler rate, Doppler shift, carrier phase, code phase, as well as signal amplitude can be simultaneously estimated through the MLE when the SLCI is implemented. Then we compare the open sky experiment results and simulations. Experimental results prove that receiver converges quickly around 2 seconds from a manually ended large error. That is 45 hertz. The simulations show that the baseband MLA can maintain high accuracy within 200 hertz initial frequency error. This slide shows a testing environment, sky plot, and the carrier to noise density ratio level of indoor experiment. So we can find that this is a very light indoor situations. There are some periods that received signal strength only ranges from 20 to 30 dB hertz. That is very weak. Here are the results. Compared to a traditional closed loop receiver with a 20 millisecond coherent, the baseband MLE efficiently denoys the Doppler frequency here and the code phase error. Then, to summarize the super resolution GNSS receiver for indoor positioning, at first, we use an SLCI to mitigate multipass interference, and it can achieve a very high sensitivity for weak signal reception. Then the digital fractional Fourier transform is used to compensate the signal dynamics. After the digital FIFT block, an MLE estimator is adopted in the baseband processing, so it achieves a faster convergence, and it can tolerate large frequency error, and it can optimize the absolute code phase error. It is worth mentioning that in this tutorial, the results is based on a very high quality clock, but low quality clock will be tested soon in the future. So finally, I'm going to summarize this tutorial. So for the objectives of this tutorial, it aims to achieve an accurate indoor GNSS absolute positioning. We mentioned that the indoor GNSS signals is very weak to receive, and the multipass effect is very severe. Extending coherent integration time can solve these two problems, but it brings new issues. For example, the bit size transition problem, and the loop filter bandwidth limitation, and also the signal dynamic problems, as well as the absolute code phase error problem. There are some opportunities for the indoor GNSS receiver. For example, we can use a modernized GNSS signal with pioneer channels to naturally remove the bit-time transition problem. Then there are an increase of the indoor GNSS market. Also, some startups can be the inspiration that it's time to develop the indoor GNSS receiver. So for this tutorial, we propose that a super resolution GNSS receiver can achieve this goal. At first, we use a very super long coherent integration to enhance the weak signal reception and to mitigate the multipass effect. Then the digital fractional Fourier transform is supposed to remove the signal dynamic problems in the non-coherent integration. Then a slam-shot baseband maximal likelihood estimator is proposed to reduce the computational load of the fractional Fourier transform, and also with a purpose to simultaneously estimate the frequency shift error, frequency rate, absolute frequency error, signal amplitude. So that's everything for today's tutorial. And please feel free to contact me at this emails, and I'm very pleased to answer your questions and have some discussions about today's topic. So thanks for your attention.
Okay, thank you, Lo. Any questions? Questions? Okay, thank you, Lo, again.
Thank you.
Thank you. Thank you. I think this morning we have 3 tutorials, three wonderful reports. That's I think this afternoon at maybe 1:30 this afternoon, we'll have our open ceremony for the IPN, formal open ceremony for the IPN conference. Okay, welcome all of you participate in the this afternoon's event. Okay, thank you, Luo, thank you, Wen, and thank you, Zhang, for your wonderful report this morning in room B. Okay.
Thank you so much for inviting us.
Thank you.
Thank you.
Welcome all of you come to Beijing for a visit to our institute if you have chance. Okay.
Sure, of course.
Okay.
Thank you for invitation.
Okay. Thank you. Then,
thank you.
If your audience have no further questions, I think maybe we can close our tutorial in room B this morning. Okay.
Okay. Thanks so much.
Thank you. Thank you so much.
Yeah, see you later.
So much. See you.
See you.
Thank you. Okay. Thank you.